Space probes use high-efficiency engines called ion engines. In an ion engine, electricity is used to knock electrons off an atom. Then, an electromagnet is used to accelerate the ion away and produce thrust. Ion thrusters usually use xenon as their propellant choice. Xenon is used because it is a noble gas and will not react with the rest of the spacecraft and destroy it. Xenon is used over the other noble gases because the amount of energy required to ionize an atom decreases when the atomic mass number increases. This is because the higher the atomic mass, the more spread out the electrons are. This makes it so that the electrons on the edge are barely connected to the atom and can be easily knocked off. The other two noble gases that are ahead of xenon are not used because they are radioactive and will decay over time. In terms of performance, xenon's higher mass gives it more thrust but less specific impulse than its lower mass counterparts. This is okay because probes can barely generate the electricity required to keep an ion engine running, and if you increase the electricity required, then you would run out of electricity. Also, ion engines have basically no thrust, so any increase in thrust is desirable. This makes xenon very good when compared to other noble gases, but natural gases have the highest ionization energy of any element group on the periodic table. Cesium has an ionization energy that is 1/3 that of xenon's. This makes it great, but it was tried, and the thrusters did not last very long because the cesium started reacting with them. In theory, the best chemical rocket propellant is metallic hydrogen. In a reaction between hydrogen and LOX, the net result is 10 megajoules per kilogram of propellant expended. But in theory, if you reacted atomic hydrogen with atomic hydrogen to get H2, then the net result would be 216 megajoules per kilogram of propellant expended. The exhaust gas in this theoretical reaction would also be H2, which has a very low molecular mass, so the specific impulse would be much higher. The problem with that is that you can't store atomic hydrogen with other molecules of atomic hydrogen because it just reacts into H2. This is where metallic hydrogen comes in. Metallic hydrogen, when stored, forms a lattice of hydrogen molecules that will not react with each other until separated. This allows you to store atomic hydrogen. Metallic hydrogen has been produced, but it is very expensive to make and it is time intensive. A team of researchers produced metallic hydrogen by squeezing solid hydrogen in a diamond anvil. The anvil used synthetic diamonds that were coated in alumina, so that the hydrogen couldn't get into the diamond and fracture it. In a couple decades, metallic hydrogen may be the fuel that is used in rockets, but for now, it is too hard to produce. Another theoretical propulsion system is a nuclear pulse propulsion system. These were being designed by people at Project Orion in the late 50s and early 60s. In a nuclear pulse propulsion system, small atom bombs were exploded near a plastic of some kind. The explosion vaporized the plastic into lightweight particles such as carbon and hydrogen. The particles are accelerated by heat into a pusher plate. When they hit the pusher plate, they move it forwards. The equal and opposite force produced by the pusher plate is converted into thrust using shock absorbers. The pusher plate is ablatively cooled using a graphite spray. The graphite is resprayed between each blast. Every second, a new atomic bomb is fired in the combustion chamber. But the blast never damages the combustion chamber because the plastic surrounding the bomb absorbs it. In theory, each blast would produce a total change in velocity of 30 meters per second. This would amount to 30 meters per second squared of acceleration, or an acceleration equal to 3 times gravity at sea level. This design would have a maximum specific impulse of 10,000 seconds. But most designs peaked at about 2,000 seconds because they couldn't have a large enough pusher plate. Ultimately, Orion lost funding because NASA thought that if a vehicle with a nuclear pulse propulsion system crashed into another country, that would be bad press. But if that didn't happen, we would be flying around using nuclear pulse propulsion systems. Another nuclear-powered engine concept was NERVA, which stands for Nuclear Engine for Rocket Vehicle Application. The basic principle behind NERVA was that hydrogen is pumped over a nuclear reactor, causing it to gain heat and pressure while cooling the reactor. Then the hydrogen gas is ejected out of a nozzle where it produces thrust. These engines have much lower specific impulses and thrusts than the nuclear pulse propulsion systems, but they are much more realistic engines. No nuclear pulse propulsion system was ever produced, but a NERVA was. To pump the hydrogen, small quantities of hydrogen are run over a reactor prior to ignition. This hydrogen then evaporates and powers a turbine. The gas that ran the turbine is then vented into an exhaust pipe. The hydrogen is also pumped through other parts of the engine to cool them. First, the hydrogen cools the nozzle, then it cools the fuel tank, and finally it enters the reactor. The fuel tank needs to be cooled because the radiation from the reactor will start heating up the fuel tank. This assembly produces somewhere between 800 and 1,350 seconds of specific impulse. This engine is more efficient than a chemical engine because in a chemical reaction you need to spend energy so that you can break apart molecules before you can combust them. Also, in a chemical reaction, the exhaust products are larger because two gases were merged to make larger ones. Nuclear pusher plate engines are more efficient than NERVAs because atomic bombs are very powerful. Nuclear reactors are essentially controlled atomic bombs. They are controlled in ways that limit the thermal energy output by making the reactions less efficient. Metallic hydrogen engines would theoretically have higher thrust than NERVAs, but they would also be less efficient. The NERVA engine concept is cool, but while the engine was made and tested, it was never flown because they were shut down by the Nuclear Test Ban Treaty, so you have to take all of this with a grain of salt. However, DARPA has put out a contract for something called DRACO. DRACO stands for Demonstration Rocket for Agile Cislunar Operations, and it is supposed to be powered by a nuclear engine. Now, of course, you might be wondering, why does specific impulse increase in a vacuum? Well, first of all, vacuum-optimized engines can be used in a vacuum. They result in an increase of performance because of their larger nozzles. Larger nozzles create an increase in performance because once the gas leaves the nozzle, then it just spreads out and stops going in the correct direction. So, larger nozzles are actually able to turn the gas into thrust for more time, so they produce more thrust. They can only be used in a vacuum because at sea level, the ambient air pressure would exceed the pressure of the gas at the bottom of the nozzle, so the outside air would start squeezing the exhaust and it would create shock waves. Of course, there is also a performance increase for non-vacuum optimized engines. This happens because rocket engines are massive pressure machines. The gas in the combustion chamber is extremely high pressure and it wants to move towards lower pressure areas. The speed at which it does this is dependent on the difference between its pressure and the outside air pressure. This is because fluids always want to achieve an equilibrium in pressure. This is because the amount of time that it takes for the fluid to flow from point A to point B will always be the same. And if more fluid needs to go through the same place in the same time, then it needs to go faster. This results in an increase in thrust, and since specific impulse is equal to thrust divided by mass of propellants, then the specific impulse will increase. Now time for some information on orbits. Orbit is a state where an object's horizontal velocity is so high that it can circle a celestial body without hitting that celestial body or entering its atmosphere. Most orbits are depicted as being elliptical shapes that never change. That is only true in a two-body system with only a celestial body and another object. In real life, there is more than one celestial body, and these celestial bodies exert gravitational forces on other objects even while that object is outside of its sphere of influence. A sphere of influence is an area around a celestial body where its gravitational field is the strongest. This is how tides are created. Tides are created when the moon's gravity pulls the water from Earth towards it. This kind of problem is called an n-body problem. N-body problems are the way objects' gravities affect each other. The effects of an n-body problem are not easy to compute. The work done about n-bodies is brute-forced by massive computer programs. This knowledge can be used to figure out how to get a craft from one place to another quickly. For example, if you position a capsule in the exact correct location just outside of Earth, then it could be sent to Jupiter and beyond just using the effects of n-bodies. More realistically, you could send a capsule almost all the way to Mars and then let Mars pull the capsule in using gravity. Most simulations of n-body effects are done using the Barnes-Hut algorithm. When using a Barnes-Hut algorithm, an object in space is picked. That object's path is being computed using the n-body effect. Then, all the three-dimensional space near the object is divided into 8 equal cubes. Often, this is a whole galaxy. The side of one of those cubes is divided by the object's distance from the cube's center of mass. If the result is theta, then the cube stays the same. Otherwise, it's divided into 8 new cubes. Theta is any number that the programmer chooses, which is usually about 1/2. This process is continued for each cube. If a cube ever has only one body in it, then it will stop being divided. After that is done, the center of masses for each cube are treated as single bodies with a mass equal to the total mass of the bodies in the cube. And then you can use this mass and position data to figure out how it affects the object of your choice. Docking ports are devices used to attach one or more spacecraft in orbit. Many docking ports contain a lance and a hole. A lance is a metal rod that has varying widths throughout it. It is small at the base, then widens. During docking, spacecraft position themselves so that they are pointing towards each other. Then, they move towards each other. Each of the lances goes into the opposite craft's hole. Then metal caps latch onto the lance and prevent it from moving around in the hole. After that has occurred, the spacecraft are docked. Once the spacecraft no longer need to be docked, they can open up their caps and separate. Docking is used to construct one spacecraft out of many. This is how the ISS was made. You can also have docking ports that use electromagnets. A problem that all rockets encountered is fuel sloshing. Fuel sloshing is when the movement of the rocket causes the fuel to move. This movement can exert an equal and opposite force on the rocket because of Newton's third law. It can also offset the center of mass for the rocket so that the engines are not pointing through it. This would cause the rocket to turn. Most rocket companies solve this problem using fuel rings in the tanks. These act as a lid and prevent the fuel from sloshing around, but these rings are heavy. Other people are saying that the real solution is to change the flight path of the rocket so that it minimizes sloshing.